These presentations are a part of a WEC-Sim Advanced Feature training course. In this presentation, I'll describe WEC-Sim's nonlinear hydrodynamics implementation. WEC-Sim has the option to include two nonlinear hydrodynamic forcing terms when solving the system dynamics for WECs: nonlinear hydrostatic restoring forces or nonlinear Freund-Krylov forces based on the incident wave. A weakly nonlinear approach is applied to account for the nonlinear hydrodynamic forces induced by the instantaneous water surface elevation, body position, and geometry of the floating body. As linear wave theory is used to determine the flow velocity and pressure field, the values become unrealistically large for wetted panels that are above the mean water level. To correct this, the Wheeler stretching method is used, which forces the water column, based on the instantaneous wave elevation, to have a height that equals the water depth when calculating the flow velocity. This method is not intended to model highly nonlinear hydrodynamic events such as wave slamming or wave breaking. For the nonlinear hydrostatics calculation, the pressure on the wetted surface is calculated based on the mean free surface elevation. This ensures the wave amplitude is not accounted for twice in the summation of hydrostatic and Freund-Krylov pressures. WEC-Sim's nonlinear hydrodynamics option can be used by setting body.nonlinearhydro equal to 1 or 2. Nonlinear hydrodynamics is now a body-specific parameter. In the input file, the flag is defined as 2 in this case. Typically, nonlinear hydro equals 2 is recommended if nonlinear hydrodynamic effects need to be accounted for. Nonlinear hydro equals 1 only considers the nonlinear restoring and Freund-Krylov forces based on the instantaneous body position in the mean wave elevation. Nonlinear hydrodynamic calculations can be very computationally expensive and dependent on the mesh resolution of the bodies. An option is available to reduce the nonlinear simulation time by specifying the nonlinear time step, which can be a ratio of the system time step to decrease the computational time required. This is defined in the WEC-Sim input file. WEC-Sim's nonlinear hydrodynamic option may be used for regular or irregular waves, but not with user-defined wave elevation, using the elevation import wave type. To use nonlinear hydrodynamic options with user-defined waves, convert your user-defined wave elevation to the frequency domain with the corresponding phases for each wave component. Then, using spectrum import, you can use the nonlinear hydrodynamic options. The reason for this implementation is that the individual wave components, which is amplitude, frequency, and wave number, that comprise the user-defined wave need to be known in order to estimate the incident wave pressure on the wetted surface of the hydrodynamic body. Refer to the developer manual for more detailed documentation on WEC-Sim nonlinear hydrodynamics. When the nonlinear option is turned on, the geometry file, which is an STL mesh, is used to discretize the body surface over which the nonlinear pressure forces are integrated. Previously, the STL mesh is only used for visualization in the linear simulations. STL meshes have been chosen because they're very frequently used across the engineering space. STL meshes can be saved as both ASCII or binary representations. WEC-Sim and MATLAB accept both. In WEC-Sim's linear implementation, the STL mesh is only used for visualization and does not require a high mesh quality. Since the mesh in the nonlinear implementation is now used to calculate the forces on the body, we will require a high-resolution, uniform mesh, as shown here. Here we can view the other bodies within the dual-flap floating OSWEC system. A high-resolution mesh is required for all hydrodynamic bodies for which nonlinear effects are being accounted. Simulation accuracy will increase with surface resolution, but the computational expense will also increase. There are a variety of software packages available to generate STL meshes, but it's critical to verify the quality of the mesh before running WEC-Sim with Nonlinear Hydrodynamics. Commercial tools like Rhino or Qubit can create STL meshes, as well as free software packages in Python like PyGmesh, Gmesh, or MeshMagick. An example within the WEC-Sim applications repository demonstrates the use of nonlinear hydrodynamics in WEC-Sim using a heaving ellipsoid. This is a sample of the WEC-Sim input file required to run the heaving ellipsoid application case with nonlinear hydrodynamics. The typical simulation class, wave, and body class parameters are defined in addition to specifying the nonlinear time step within the simulation class and defining the nonlinear hydrodynamics option used for the body. The Simulink block for calculating nonlinear hydrostatic restoring forces takes in geometry information, wave density, gravity, body parameters, and calculates the nonlinear buoyancy forces on the body. Similarly, the Simulink block for calculating nonlinear Freud-Krylov forces points to a MATLAB function which takes in the necessary Simulink variables and calculates the nonlinear force on each body. The nonlinear hydrodynamics option in WEC-Sim can save the pressure distribution over the meshed body. To reduce the output file size, it is recommended that the pressure distribution is not saved to the mat file by default. For multiple condition runs, it is recommended to save the selection of data required from each simulation using the user-defined functions MCR file. Additionally, if the body geometry is symmetric along the incoming wave direction, it's recommended to use the 3 degree of freedom constraint instead of the 6 degree of freedom constraint. This will reduce potential numerical instabilities, especially when nonlinear hydrodynamics is used. Thank you for listening. View our documentation for additional WEC-Sim training course webinars.